Now, I believe that this idea of force over area is critical because from this idea of pressure, we're going to now derive what is known as the ideal gas law. Now, this might be a little backwards and maybe your textbook or your professor may be showing you, right? Because normally when you look at, let's say, your typical textbook, they'll walk you through all these different smaller laws of gases or these smaller observations that gases do before they kind of put it all together in this nice neat package. But instead, I think the ideal gas law is so critical and it's so important that I'm just going to jump right to it and we're going to go from there. So here's how we're going to derive our ideal gas law. We're going to start off by talking about the physical equation, right? Our physical equation of pressure. And so what we see here for pressure is that pressure is going to be nothing more than a force being divided by an area. Now, you may have learned in middle school about forces, and you know that a force is nothing more than a push or a pull. But in order for me to push something or to pull something, what I'm really doing is I am exerting a mass and I am accelerating that mass. So really, a force is nothing more than mass times acceleration, right? And then, of course, we're going to have our area. And again, area could be in centimeters squared, meters squared, whatever you want to call it. Okay, now this, what I've just written out right now, is my physical equality. Notice I'm saying that it's an equality. This means that literally pressure equals all the things on the right-hand side. The problem is that when we're talking about gases, I don't know about you, but how do I measure the acceleration of a particle? I mean, I'm sure there's a way, but if I'm talking about a gas in general, to be able to break it down to an individual particle, that seems kind of hard to me. That's not something that I would intuitively be able to say something intelligent about. You know, the other thing I think about is that when I think about a pressure of a gas, I think of a container, not like a square, not a rectangle, not like the sides of the container. I think of the whole thing, like a 2-liter soda bottle, or an oxygen tank, or a dive tank that a diver puts on, right? And I think of some three-dimensional object. Well, how is volume and area related? Is volume and area the same thing? And the answer is no, it's not. 2 dimensions versus 3 dimensions. So here's what I'm going to do. I'm going to take our pressure equation, what we have right down there, and what I'm now going to do is, instead of talking about it from a physical term, what it actually is, I'm going to kind of set up some relationships or some mathematical commonalities that we see between the two. As an example, does area equal volume? No. But the larger the surface area of a particular container is, don't you think the volume is also going to increase, right? So let's think along those lines. And so what I'm now going to do is, instead of talking about it from these exact equalities, I'm going to come up with other variables that are similar, but not quite exactly what the definition of pressure is going to be. Because it's no longer an equality, I'm going to drop for a moment the equal sign, and I'm going to replace it with my little fishy. And here's what my little fishy represents. It represents is proportional to, okay? So it's related to, it's proportional to, okay? But it is not equal to, right? So pressure is proportional to, all right? So instead of mass, I'm going to measure amount of the gas. Now, as soon as I say amount, in your head, you should be like, ooh, 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 that sounds an awful lot like moles, right? So again, can I use the mass to figure out the amount of gas present? Absolutely, right? But it's usually going to be easier for us to count number of particles, 1, 2, 3, 4, 5, versus, oh, we have 5 grams of a gas. Then I have to know, well, what's the gas, etc., etc. So in order to know how much gas I have, the amount of gas I have, I'm going to work in moles. Does that mean that mass equals moles? No. But if the mass goes up, chances are the number of moles will go up, right? Next, let's tackle this acceleration one, because this one is really tricky. How am I going to measure the individual acceleration of individual particles? Let me help you. We're not. At least not in a way that's going to be simple for you and I to calculate quickly. So instead of worrying about the individual speed of every single particle, what if I could kind of cast a broad net and capture a bunch of particles? In other words, instead of talking about this through the lens of individual acceleration of individual particles, I'm going to talk about it in terms of temperature. All right. Now, temperature is equal to the average kinetic energy of a substance. So notice a couple of things. I did not say the word acceleration anywhere in that definition. Temperature is equal to, or temperature is, the average kinetic energy of particles in a substance. Now, what that means to me is that as the temperature goes up, the overall average kinetic energy goes up. In other words, as the temperature goes up, the particles seem to be moving faster and faster and faster and faster. Now, and here's the big if the particles are moving faster, then aren't we likely to have, on average, greater accelerations? And the answer is yes, right? Now, does that mean that just because temperature is higher, every single particle is going to have a greater acceleration? No, we're not saying that. What we're saying is that there is a relationship between the temperature and the acceleration. And what I think it is that as the temperature goes up, the acceleration of the individual particles goes up as well. So not that they are equal, temperature does not equal acceleration, but it's definitely related to it. And last but not least, we're going to divide all of this by, as we spoke at the beginning, our volume. Now, why did I choose these three particular variables? Because what we find is that the pressure that a gas exerts at the end of the day is going to be defined by these three factors. How much of the gas do you have? How many moles? The temperature of the gas, how fast are the particles moving within that gas? And finally, the volume that the container occupies, right? Or excuse me, that the gas occupies. The bigger the volume, the lower the pressure. Kind of makes sense. The more space the particles have to spread out, they're going to hit the sides with less force because there's going to be less of them at a particular moment hitting the sides of the container. So, if pressure is related to moles, temperature, and volume, is there a way for us to start setting up equations? And the answer is yes. But before we do that, we want to take a look at what my variables are going to be. So, typically, when we talk about the relationship between pressure, moles, temperature, and volume, pressure is going to be the variable P. Moles is going to be lowercase n, as in Nancy. And then we have the temperature and my volume. Now, since this is not an equality, I cannot say pressure equals moles, temperature, and volume. That's not true. But what I can say is that there is a relationship between all four of them. And the way I can create that relationship is I'm going to literally move everything to one side. And when I move everything to one side, I get the following. I get that pressure times volume over moles and temperature will now equal some constant, will now equal some value. And all that this means, so that you and I are clear, is that when I now have the pressure being multiplied by the volume divided by the amount of gas and the temperature at which the gas is at, whatever those values were, whatever the pressure was, the volume, the moles, temperature, whatever that is now going to produce a ratio. And that ratio, which we're going to term R, is going to be our gas constant. And our gas constant is going to be nothing more than at a given pressure and a given volume and a given amount and a given temperature, what that ratio between pressure, volume, moles, and temperature is going to be. And so in our next episode, we're going to start to develop this ideal gas law and how it evolves from here.
So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.